So let's talk about half-life really quickly. Often written as like T sub 1/2 is a common descriptor. We like to use it to sort of compare relative reaction rates. And examples are radioactive decay, or also sort of drug decay in the body. Okay. It is the time required for half of the initial reactant to be converted to product, or in the case of the body, maybe just how long would it take for half of this drug to basically become non-functional, as it is no longer working if it was just floating there, not binding or doing what it was supposed to. Okay, so then you set A equal to A naught divided by 2. Right? Because you're interested in half of the initial concentration. So whatever you started with, you're generally solving for a time t, this half-life, solve for time t, where it satisfies that this concentration you've reached is half of your initial concentration. And you can solve for t using any of our previous integrated rate laws. Okay, and this will just depend on the nature of the decay. So you would have to sort of be told whether it decays with first law kinetics or second order kinetics or zero order kinetics. Some other information would have to be made available for you, like for you to know that. So for 0th order, you could just have T1/2 is equal to initial concentration divided by 2. Okay. For first order, if you plug this into the integrated rate law, you're going to get the natural log of 2 over k. For second order, you're going to get that T1/2 is equal to, this is T1/2, is 1 over k times A naught. So first order is a unique case then, where here is time, and here's concentration, and we know that it has exponential decay. So essentially, at the first half reduction in concentration, this is T1/2. And as you go to the next one, so go down by another half. My drawing is not perfect, but this T1/2, these two things should be equal, okay? For a first order decay, the half-life is the same every time. It's not changing. It's a constant related to your rate constant K. Whatever your rate constant K is, it's natural log of 2, which is 0.693, if you want to remember it, divided by your rate constant. But this is not going to be the case for, say, 0 order. So this was first order, but for 0 order, half-life is changing, okay, with time. So we have a linear drop-off like this. So for sort of our first half, we have our first half-life. And as we go to our second half-life, this size here and this size here, this is smaller now. Okay? So half-life is changing as the concentration changes. Okay? And so we can sort of see that by inspecting these relationships, right? That is concentration, because your initial concentration now is half as much as you started with, so half-life is changing with time for 0 order or second order. First order, half-life is a constant related to the rate constant.